Hello, everyone. We are building a museum of computer technology in the age of AI. AI knows everything, yes, I know, but it also has everything the algorithms, the infrastructure. So, if one day AI writes down some code that threatens people, I hope at least one of you still understand it and pull the plug. Topic 1: Dynamic Programming. Let's start with something simple, calculating Fibonacci numbers. You might think, why should I care about this math puzzle from middle school? But watch what happens when we try the obvious solution. Let's see, f5 is equal to f4 and f3. Then f4 is equal to f3 and f2. And f3 is equal to f2 and f1. And so on. This recursive code is beautiful, elegant, mathematically pure. However, it's very slow. Why? In the recursive code, the final problem is divided into small ones, say subproblems. However, the subproblems are calculated repeatedly. This is the disease that dynamic programming cures, not just for Fibonacci, but for thousands of real-world problems. Route optimization, resource allocation, machine learning optimization, and so on. This pattern is always the same. When you find yourself solving the same subproblem repeatedly, you are leaving exponential time on the table. Now we are going to take this exponential nightmare and turn it into something that runs in linear time, not by being clever, but by being systematic. We have known the structure fn depends on fn minus 1 and fn minus 2. Step 2, we define our state. dpi is the Fibonacci number with the index of I. The next step, the magic. dpi equals dpi minus 1 plus dpi minus 2. We have turned this recursion into a simple formula, which is easy for the computer. And step 4, base cases. dp0 is 0 and dp1 is 1. These are the seeds from which everything grows. The final step, we compute bottom up. In this code, we start from the base. Compute each number exactly once. The secret is just this, remembering what you have solved. Now please read each line of the code and try to understand the whole process. Now let's see what happens. And in the graph, we can see because of the DP array, we have memorized the average sub solution. I mean, the best solutions for subproblem. So each subproblem is solved exactly once. And then we can do it even better. In this part, we can see because we only need the previous two values, we can reduce the space to 01. It's amazing. Just like this, because we just use the last two ones, and we use two variables rather than an array here. So the space is reduced to 01. There are some core concepts you need to know about the best solutions of the subproblem. For example, if the shortest path from A to C goes through B, then path A to B must be the best solution from A to B. Path B to C must be the best solution from B to C. About the overlapping subproblems, please remember, dynamic programming usually says, hey, I have already solved this before. I will just remember the answer and reuse it. There are two ways to use dynamic programming. They just go in opposite directions. The first one, top-down. Start with the big problem, break it down using recursion, and store answers to smaller problems as you go. You only calculate what you actually need, kind of like lazy computing. And the bottom-up one. Start from the smallest, simplest cases and build your way up, step by step, until you reach the final answer. It takes more steps, but often uses less memory and avoids the overhead of recursion. For those who think mathematically, here it is. Basically, it says the best value in a certain state is equal to the best action's reward, plus the future value you get afterward. And this is the same secret that powers reinforcement learning, the reason why AlphaGo can beat humans and self-driving cars can decide what to do next. And the typical dynamic programming problem has this mathematical structure. It always changes big problems to smaller ones. And then it's kind of combination of sub-problems solution to the final answer. This table shows different problems follow different patterns, like linear combination problems, optimization problems, two-dimensional grids problems, and interval splitting problems. Should we memorize all these stuff? No. Should we recognize them? Absolutely, yes. When you see a new problem, ask, which pattern does this follow? That recognition turns a 45-minute struggle into a 5-minute solution. This is our toolbox. 5 questions that transform confusion into clarity. Step 1. Define the state. This is the most important step. Ask yourself, what information do I need to track? Write down every state we need. And then find the relation between states. Ask yourself, how does state I relate to previous state? Step 3. Identify base cases. In other words, what are the smallest problems you can solve directly? And step 4, determine the computation order. This is where beginners get tripped up. You must ensure when you compute DPI, all the dependencies are already available. The final step, extract the answer. Where is your solution? Sometimes it's DPN, sometimes max DP. Sometimes you need to reconstruct the path by backtracking through your choices. Know where you are going before you start building the table. Now we talk about the different patterns of DP problem. There are 6 major patterns that cover 90% of DP problems. The first one, linear DP, we have learned it. It's foundation of everything. Then the pattern 2, two-sequence DP. It's comparing or combining 2 strings or arrays. State DPIJ considers first I elements of sequence 1 and first J elements of sequence 2. And the third one, knapsack problems. It's very famous. You have a capacity constraint and items to choose. Pattern 4, interval DP, problems on ranges or substrings. The state DPIJ stands for the interval from I to J. And the next one, tree DP. The problem is defined on a tree structure. You use DFS plus memoization. Each node's value depends on its children. And the last one, state machine DP. Multiple states with transitions between them. Each state has its own DP array. Now let's talk about something that confuses many people. Why this time complexity? The formula is surprisingly simple. Time equals number of states times time per state transition. Oh, it hurts. And there are some examples in the table that we haven't learned before. So if you guys are interested in the details of all these difficult problems, please tell me in the comment area. Now, space complexity. The naive approach is size of DP table, but often you can optimize it. Space optimization is about understanding dependencies. What do you actually need to remember? And here's the trade-off. Space optimized code is harder to read, harder to debug, and harder to modify. In an interview, get the right solution first. Then, if asked, optimize space. Let's try to understand more. Remember that tree, the recursive tree in the Fibonacci? If there's no storage, everything is computed so many times. And it means creating exponential branching. This is a training roadmap and more than 20 problems organized by difficulty. And there are 3 levels. For beginners level, this teaches the fundamentals. And don't skip this thinking they are too easy. Master them until the pattern is muscle memory. Understand not just how to solve them, but why it works. And the second level, this is where we build pattern recognition. And these are interview favorites. And the last level, these separate good from great. These require deep understanding. Don't just code them. Trace through examples by hand. Understand every state transition. And following the roadmap, okay, forget the week number. Feel free to take time to learn enough. For example, 3 months,